Hey, what's up, everybody? We're going to be talking about elliptic curves today. In this first video, I'm just going to be talking about the mathematical basics of an elliptic curve, and then in the follow-up videos, I will be talking about how they're used in cryptography and particularly the Diffie-Hellman key exchange. But to get started, let's talk about an elliptic curve from the algebraic perspective. So an elliptic curve is defined as the set of points or the set of ordered pairs x, y satisfying such that y squared equals x cubed plus ax plus b. And you might ask, what are the numbers x, y, a, and b? Are they fractions? Are they numbers? Well, they all have to belong to a field called K. And this field K could be anything. For our purposes, we're going to start and look at elliptic curves over the real numbers, but K could be the complex numbers, it could be the integers, it could be the rational numbers, or it could be a finite field, which is basically the integers mod a prime number. We'll get into a lot more of that in the later videos. Okay. So enough of the algebraic stipulation. Let's look at the geometric graph of the curve, which will kind of drive the entire video. So typically an elliptic curve looks something like this. Again, so basically based on our algebraic definition, let's just take a sample curve. Let's do like y squared equals x cubed minus 5x plus 12. And you can see this factorization is something like x cubed minus 3x plus 4 times x plus 3. And so it has a 0 at x is equal to -3. This is the x-axis, and this is the y-axis. And so any point on this curve, like P right here, basically the xy coordinates of P satisfy this equation right here. Okay. Why elliptic curves are useful and used a lot in cryptography is because they have the properties of a group. So elliptic curves can be thought of as the mathematical construct of a group, which, if you're not familiar with, is a set of elements where there is a binary operation called the group operator defined such that basically you give the group operator any two elements from the set, and it gives you a third element that's also in the set. To make this point clear, maybe let's just look at the integers. So in this case, we're all familiar with the group operator here. It's plus, right? The addition operator. So -2 plus 5, for example, gives us 3. And the real numbers, let's take, so the real numbers with multiplication, this is a group operator here. So -2 times 5 gives us 10, right? So we know how the plus operator, the group operator in the integers works. We know how the multiplication operator, the group operator in the real numbers works. And then the question then is, if elliptic curves are also a group, how does the group operation plus work in this scenario? So to do that, let's think about the two things that we're trying to add, right? So we need two elements. So the two elements are points on the elliptic curve, P and Q. So let's put, let's put P right here, and let's put Q like right here. Okay, and so then we ask, what is P plus Q? And the answer to that is best seen geometrically. So what we'll do is we'll draw a secant line. If you're not familiar, basically the secant line is the line that goes through the 2 points, P and Q. So going through P and Q. We'll call this line L. And whenever we have a line like this on an elliptic curve, you can think about in the general case, not all the time, and we'll cover that some specific cases, but in the general case, whenever you have two distinct points, P and Q, and you draw a secant line through them, what will happen is that line L will intersect E at another place, and we'll call that place R, okay? And P plus Q does not equal R, it actually equals the reflection of R over the x-axis. So this is the x-axis, this is the y-axis, and so let's call this point, so this point right here, the reflection of R over the x-axis is what's defined to be P plus Q. So let's just call this point S for some. So again, for the elliptic curves to be a group, what we need is some form of a group operator, some form of addition. And if we treat points on the elliptic curve as like elements in our set or elements in our group, the addition operator is then defined as the point you get when you draw a secant line through the two points you're trying to add, P and Q, and then that resulting point R, reflecting it over the x-axis. That point is P plus Q. Okay, and this begs the question, so we know what P plus Q is when they're kind of like distinct points. What about P plus P? So what about 2P? And we can also do that. So same setup. We have the elliptic curve E, have our x-axis, we have our y-axis, and sort of the best way to think about this is, let's say we have, P right here, and we have Q right here. Let's not call this Q, let's call this Q1. And again, what we're going to have is we're going to have our secant line. This is a straight line, so let's make it a little bit straighter. So L1, and we're going to draw our point R1 where it intersects E again, and then obviously P plus Q1, we'll call that S1, is down here, which is R1 reflected over the x-axis. Now we can think of this sort of in a calculus-y way. Think of us taking Q and we're pushing it closer to P, and we're seeing how that affects our sum S. Okay, so maybe we'll have Q2 right here, and then that line will go something like this. So that's L2, this is R2, and this is S2. And you can see basically what we're getting at is as Q approaches P, what we're going to have is a tangent line rather than a secant line. So the tangent line will look something like this, and we'll call this one L, and this is R where it hits the E again, the elliptic curve, and then the reflection of it S down here, that will be what is P plus P. So in the case of P plus Q, we just draw that secant line, find that resulting point R where it hits the elliptic curve again, then reflect it to get our S. In the case of P plus P, where we're adding the point to itself, all we're going to do is we're going to draw the tangent line, and then we're going to see where it intersects the curve E, and then reflect that over the x-axis. A couple things to note. There is one special case. So if we draw our elliptic curve again, so this is X, this is Y. Let's say P and Q right here. So basically they lie perfectly on a line parallel to the y-axis. In this case, there is no third point of intersection to find R. So there's a special notion of what the sum of P plus Q is in this case, and that's called the point at infinity. At infinity. And it's usually denoted by this character, And basically, it has these following properties. P plus the identity element gives back P, and P plus Q, specifically in this setup, gives us the point at infinity. So you can think of it as sort of like a zero element or maybe an infinity element, but point being, having this particular element in conjunction with the rest of the points on the elliptic curve makes it a group and makes all of the math work. Again, for a group, a set G to be a group, it needs to have three properties. It needs to be associative, which means A plus B plus C equals A plus B plus C. It needs to have an identity element, which basically means if you take a point in your set and you add the identity element to it, you should get the original point back. And finally, there should be an inverse element, which means whenever you have a point P, there should exist some other point minus P, where if you add P plus minus P, you will get back the identity. And so in this case, Q is the point minus P, such that when you add Q to P, you get back the identity. Anyways, having this identity element in the in conjunction to all the points x, y, satisfying the elliptic curve equation makes it a mathematical group and allows for all the great things that we'll see in the later videos. So to recap, what we did is we defined the elliptic curve. So it's a set of points x, y, such that they satisfy, in our particular case, I'll use the specific example, y squared equals x cubed minus 5x plus 12. And so this set of points in conjunction with that extra identity element, so that is, or the, sorry, not the, yeah, the identity element or the point at infinity, this is a mathematical group and gives us all the good things we need for the cryptography. In addition, we also discussed the group operator, so how to get P plus Q and how to do 2P. And yeah, that's all we're going to talk about in this video. But go ahead and look at that next video for more on elliptic curves and how they're used in cryptography. Thanks for watching.